flamingos feeding on algae and plankton from the water and mud of a lakeside. Each mouthful is squeezed through fibres in the jaw, filters that retain the food. Their feeding habits have evolved as part of the extensive food web of nature. But out of their natural habitats, flamingos can survive and prosper on an artificial diet. These artificial diets create new links in the food web, and there are far-reaching implications. There will always be competition for food, but in formulating this diet for flamingos, animal nutritionists have got both the content and the shape right. And by making the pellets the right size, the delicate filter mechanism can be bypassed. So finding out how animals eat is as important as knowing what they feed on. We'll look at the diversity of food sources and feeding mechanisms as a first step to devising new formulae for food. Let's start with the top carnivores. The tough shell of the mussel is no problem for the jaws of the wrasse. The pieces that drift away are a source of food for others. Brittle stars go wild as particles of flesh drift towards them. Once trapped, the particles are passed into the mouth by the tube feet to be digested. It goes on feeding, becoming bloated. The mussel has provided food for both, but where does the mussel get its food from? Oscillating cilia on the gills create a current of water. Particles in the water are trapped by the cilia, and mucus binds these particles into food strings, which are passed along the edge of the gills to the mouth. And in slow motion, here's the action of a single cilium. The real intricacy of the gill can only be seen with a scanning electron microscope. The cilia can trap particles as small as 1 micron across, and the food particles are plankton. They are a rich source for organisms higher up the food web to exploit, like this snake-lox anemone. Its tentacles carry nematocysts, cells which thrust out stinging threads that can paralyze and entrap their prey. The prawn, with its rapid movements and its advanced nervous systems, usually escapes the anemone's tentacles. But not always. Once caught, the tentacles guide it in towards the mouth, where it is swallowed whole. Under phase contrast, the coiled thread within an isolated nematocyst is clearly visible. During discharge, the thread is turned inside out extremely quickly, becoming a darting spear. The Portuguese man-of-war is a battery of darting spears. Beneath it trail its tentacles, loaded with stinging nematocysts. The violet snail is immune to the venom, so how does it consume its prey? Using its spoon-like foot to produce a raft of bubbles, its radula can graze on the tentacles and swallow the stinging cells which are so lethal to other creatures. Here's a closer look at how the radula works, the rasping action of rows of teeth that draw food in. Under the electron microscope, the rows of teeth on the radula are visible. As the front teeth are worn away, a replacement section moves forward. Predators use their camouflage, agility, and well-developed vision to capture prey. The cuttlefish, which is also a mollusk, has these advantages and a remarkable feeding mechanism. On this occasion, the prey is a prawn. The prawn's own agility is no match for the cuttlefish. The long feeding tentacles shoot out and grab the prey, too fast for the eye, so let's see it again. The anglerfish relies on a natural lure rather than a turn of speed to trap its prey. This fish seems mesmerized by the gently waving flag, perhaps thinking that it's a potential meal. And again in slow motion. We've come to the top of the food web, and we've learned various tricks from nature in order to feed ourselves. But more recently, we've formulated artificial diets to farm fish. These farms help provide the large quantities of food required by our increasing populations. But matching the nutrients of nature is a substantial challenge. The trout has a varied diet. It feeds on insect larvae, shrimps, water boatmen, all swept towards it by the current. The trout is basically a carnivore, a hunter that eats only very small amounts of algae and weeds. Its diet is high on protein, matching its high energy requirements. To farm trout successfully requires an artificial diet that matches the high protein content of the natural diet. It also supplies a wide range of other nutrients, and the pellets must be of the right size. The fish must be grown in the right environment too. There must be an abundant supply of pure, clear water. These artesian wells provide aerated running water at a pH of 7.3, within the required range of 7 to 7.5. Being artesian water, it emerges at the same constant temperature, 11 degrees centigrade, in winter and summer, and its temperature and quality are regularly monitored. Herons are natural predators of trout, and because they congregate around the ponds in search of food, netting has been put in place to provide protection. But the major consideration for the farm is diet. A local supplier has worked out the ingredients of this diet from scratch. It obviously works. It promotes growth and leaves no residual dust that could damage the fish's gills or contaminate the pond. The Sharps, a family concern who rear trout in these ponds at Bourne End in Hertfordshire, were instrumental in the development of the diet. Some of the fish they grow replenish the nearby Tring Reservoir, and it was here that John Sharp met Michael Glasser, a manufacturer and supplier of feeds for cattle, sheep, pigs and poultry in the Hertfordshire area. Sharp suggested that it may be profitable to supply new diet food for the trout farms that were being developed in the area. Although this would be a completely new venture for Glasser, he decided to take the job on.
I looked upon it as an exciting venture. Over the years, we've produced feed for a full range of agricultural livestock, with the exception of fish. I thought it would be very interesting looking into just what was required for this new exciting industry.
By reading research papers and corresponding with nutritionists throughout the world, Michael Glasser gradually constructed his diet. To meet the high protein requirements, the principal ingredients are fish meal and fish oil, and this is supplemented by vegetable protein in the form of soya bean meal and maize gluten meal. The other proteins are provided by whey powder, yeast, meat and bone meal. The diet is completed with tiny quantities of health additives and essential vitamins and minerals. But he found there wasn't enough carbohydrate and starch within the diet to stick the ingredients together.
Normally, we rely upon heat to activate starch to produce a good firm pellet. In the case of a fish food, which is high in protein and fat, there's little natural binding agent. It's most important to produce a good dust-free pellet for two reasons. First is the economic waste from dust, and secondly, from the health point of view from the fish, because dust will badly damage the gills. We found that by introducing a higher pressure dye and by introducing the fat after the manufacture of the pellet, that we were able to achieve a better quality.
Making the pellets at high pressure improved the palatability. But what about the standard of the nutrient value of the diet? Michael Glasser's diet has earned not only the praise of nutritionists, but also a steady stream of orders from local trout farms. In Scotland, artificial diets supply salmon farms with their food. Salmon is a much wilder breed than trout, but there are opportunities to influence its maturation and growth so as to improve yields. At Otter Ferry on the west coast of Scotland, a commercial fish farm has participated in a series of experiments that link diet to development. The idea is to regulate maturation and growth by a careful restriction of the food supply during the growing cycle to see if this will improve yields. This tank contains young salmon, one-year-old smolts as they're called, that have been overwintering on a maintenance diet, and so their total lipid content decreases. Up to this stage, they live in fresh water, and there comes a crucial stage where they're transferred to salt water. After spending the winter in seawater, in April there will be a fast build-up of lipids in some individuals. These individuals will mature in the autumn and become what are called grilse. The other group in the population will not mature until a year later, and it's this maturation pattern that interests scientists who can see a potential application. Commercially, early maturation as grilse represents a loss, since the fish will not be growing and may not be at the optimal sale weight of 3.5 kilograms. For the farmer, growth is the priority, not maturation. So, can we prevent maturation from being triggered early? Scientists working in this laboratory at Almond Bank near Perth are investigating the links between maturation and growth. Can the salmon be fed a controlled diet at the critical times that will delay maturation? John Thorpe, Senior Principal Scientific Officer at the laboratory, has been working with the salmon farming industry for many years. He believes that by defining the time at which dietary restrictions delay maturation, farmers will improve their yield. And this is an experiment that tests his ideas. They've devised special covers for the fish, recreating the dark river conditions that the growing young salmon find in the wild. And by directing the water radially outwards, they distribute the fish evenly, ensuring that each individual has the same feeding opportunity. The fish in this tank are being fed half rations in March. The adjacent tankful will go on to the reduced diet in April. By using several tanks, the effects of a restricted diet on the fish can be tested from September through to May of the following year, and the precise month that delays maturation can be discovered. The food is supplied automatically as the winter progresses. Only periodic checks are made to see that food is being taken and if growth is proceeding. Is it possible that the fish can compensate for diet restrictions by simply eating more when food is available? To check, they must work out the amount of food actually being eaten, establishing the precise diet that the fish are on. By X-raying anaesthetized fish, they can calculate the reduced intake. Tiny glass beads mixed with the food show up as white spots on the photographic plates. Counting the spots gives a measure of the intake of the fish. The particles also trace out its digestive tract. The staff here at Almond Bank are developing a less laborious method of counting, which uses a video camera. An image analysis system detects the particles and automatically calculates the intake. This proves to be about 60% of the intake of the fish whose diet wasn't restricted. Do the results of this experiment tie in with the work that John Thorpe did during the previous year at the Sea Hatchery at Otter Ferry?
Well, to investigate this process a little more closely, we decided to repeat the Otter Ferry experiments here in the hatchery at Almond Bank, and this time using small freshwater stages. This time we found that in April, restricting the fishes to half ration produced the same result, but the interesting thing was that among those fish which matured, they accumulated fat around the viscera during April, whereas those that didn't mature continued to use up their stored fat at that time. Now that seems to say that when we restrict their intake, we reduce the replenishment of this fat store in the springtime. Now, we don't know how this is related to the suppression of maturation, but what we have done is to suggest that, as in higher vertebrates, the quantity of fat is closely related to the success of maturity, then maybe the same process operates in fish.
The story of how the salmon matures is emerging. The seasonal increase in day length provides the first impetus. As day length increases, the levels of the hormone testosterone rise in most of the fish. For some, the rise in hormone level doesn't occur. They don't mature that year. The maturing fish replenish their body lipid stores in April, like salmon in the wild. By reducing food intake in winter and spring, this replenishment is delayed, suggesting that there's a genetically fixed threshold. When this threshold is exceeded, the fish matures, perhaps because the quantity of fatty tissue available in spring influences the hormones that are involved in maturation. The hypothesis is that testosterone is converted into estradiol by the enzyme aromatase, which is found in fatty tissue. Estrogens are needed to stimulate the hypothalamus and the pituitary to produce other hormones which induce the process of gonad maturation. So we think that the quantity of fatty tissue available in the spring determines if enough estradiol is produced for gonad maturation to occur. If there's enough, then the fish matures, but if not, then its maturation is delayed. If this is true, then the feeding experiment should isolate critical months when reduced food intake has the greatest effect on the population, preventing maturation into grilse. In all of the tanks, despite different feeding regimes, a proportion of the fish matured. The most significant reduction occurred in the tank where feeding was restricted during February and March. John Thorpe has thought through another dietary experiment following on from this one.
One extension of this that we're looking at just at present is to see if we can go about this in a simpler fashion, if we can reduce the amount of fat stores that the fish carry into the winter with them. Now, if we cut back their intake in October, November, December, it may be possible to reduce that fat store to a point where whatever we do to them during the winter is not going to make any difference. They're not going to mature anyway. So we're testing at the moment to see whether we can control it much more simply by reducing intake in the autumn.
These experiments suggest a significant food reduction which carries no growth penalty. The saving on food supplies is a substantial financial benefit to the farmer. Further research is being carried out, but it's a promising idea that may find widespread application to the salmon and other aquacultural industries that rely on artificial diets to sustain their success, growth and development.